Hello again, everyone. My name again is Garrett Karto Keating. I am the SMA project scientist, and right now I'm going to be talking a bit about error recognition, that is, identifying problem data in your data sets in the so-called visibility domain, so kind of when the data is still raw before you get to imaging it. I'm mostly going to be talking about this at kind of a higher level, kind of philosophical level, not so much talking about implementation details or which program or which command to run in different software production packages. Mostly I'm just trying to get an idea of how do we approach data and identifying bad data in a statistically sound way. So similar to my other talks, I kind of like introducing mathematical concepts up front. I'm going to be talking about a bit about normal errors and normal distributions, and for good reason, in fact. Normal or Gaussian distributions are some of the most commonly used statistical distributions in radio astronomy and kind of astronomy writ large. The reason for that is relatively simple, kind of comes back to the central limit theorem, which basically says that if you have a very large set of samples that are drawn from some distribution, doesn't have to be normal, it can be any distribution, with a well-defined mean and a well-defined variance, the sum of all those samples, the kind of error or noise statistics on that sum, is actually converges to normal or Gaussian statistics. So we typically in radio astronomy average together millions of data points and therefore trust that a lot of our data have errors or have noise statistics that follow a normal distribution. A couple of other distributions that are commonly used, chi-square distribution, which is the sum of the squares of values that have been drawn from a Gaussian distribution. Typically you talk about chi-square distribution in terms of number of degrees of freedom, which is k shown here, or the number of independent draws that you have from your statistical sample. And finally, there's this other thing called the Rayleigh distribution. It turns out that if you have a complex random number, that is the real and the imaginary part are both random numbers that are normally distributed and whose mean is 0, if you take the absolute value of that set of random values, random complex values, they will create a Rayleigh distribution. And this is kind of powerful for when you actually have visibilities that are noise dominated. If you take the absolute value of all those visibilities, you'll get something that looks like a Rayleigh distribution. So, jumping straight into data, why are we talking about bad data? Well, the reason is simple, and it comes back to this kind of axiom that almost every advisor I've ever had has told me, which is bad data is worse than no data. And even though this seems maybe a little silly, the reason for it is actually very simple. In astronomy, we are typically looking at things that are at least thousands of times fainter than the instrument noise. And so that requires averaging together billions, trillions, or even more samples of data all together. So, as you might imagine, it doesn't actually take a whole lot of bad data to corrupt the full data set in such a way that it swamps the underlying signal, the underlying little detection that you're looking for. So we have to be very careful about the data that we carry forward, because in the end we're having to average together a lot of data to produce whether it's a spectrum or an image on the sky, image of the sky. It doesn't take very much bad data to basically corrupt that and to basically give us bad results. So there are lots of things that can potentially go wrong during the course of an observation or even the data production process that can basically render bad data. The most obvious is that we can have system malfunctions, things can go offline, things can break. The antennas are mechanical systems, they track and move across the sky. And so, we do have instances where an antenna stops because there's a motor fault and one antenna is pointing off in one direction, the other antennas are pointing off in another direction, and obviously you don't want to include data from the antenna that's not actually pointed at the source. We can actually have contaminants in the data itself. This is a little bit less of an issue perhaps for millimeter wave astronomy, but definitely for centimeter and meter wave. Human beings are very good at making radio pollution. Things like Wi-Fi, GPS, all these things broadcast lots and lots of radio waves. And those things get picked up by our radio telescopes. and can produce contaminants in the data that are millions of times or larger, stronger than anything that we're looking at. So we want to be able to eliminate those contaminants. We can have errors in things that we use to calibrate the data, whether it be gain solutions or flux scaling. All these things can inevitably corrupt the underlying data that we're trying to look at. And when that data all gets averaged together, it can limit the fidelity with which we can make scientific measurements. And finally, we can have errors or uncertainties about the actual noise in the data itself. You can imagine that if you think that a particular data set is very good, but in fact is very noisy, and you add that to a very good data set with very little noise, you add something with a little noise with a lot of noise, you'll get out a very noisy summed data set. And so you can end up swamping something that looks like it would be of interest by this little extra noise that you just didn't realize was there. Finally, I'll just point out that all these problems by themselves can create issues, and assumptions about these problems can also create their own set of issues. So sometimes it's nice to take an approach of check once or check twice, kind of critical things to just make sure that everything looked okay, looks fine. You can sometimes save yourselves a lot of headaches in processing your data just by doing some very simple sanity checks. Were the antennas pointed in the right direction, and was it looking at the source that I expected? And some of these things that are maybe just 30 seconds here, 30 seconds there, but they can potentially save you a lot of pain in the long run. So we know we've got bad data in our data set, and the question is now what to do about it. And generally speaking, the options fall into kind of one of three categories. So we can just simply discard the bad data. And in fact, this is probably the most common approach in radio astronomy and in interferometry. It does carry some risks. In particular, you may screw with the noise statistics of the data, which would be very bad. And I'll talk about that more in a little bit. But this is the most common approach. The second approach is actually just to downweight the data. So if you're uncertain about the data, or if you think it might be noisier or otherwise just not as high a quality, you can downweight that data when you come to average it together with other data. That's a perfectly valid approach, kind of very Bayesian style approach of taking your priors and applying them to the data. It is safer sometimes than just wholesale discarding data. But you can incur sensitivity losses that might be unnecessary. Finally, you can attempt to correct the data. This is definitely the most difficult task because you both have to know that there's a problem that exists and you have to know how to fix it. But it does come with the highest payoff. If you can actually fix the problem, of course, then you've tossed no data whatsoever, and you're good to basically take everything forward as you try to analyze what you've got. So, focusing right now just on the first choice, just on flagging of data, the most common approach is something like this. So you make a plot where the y-axis is amplitude and the x-axis is anything from channel or integration number or lots of quantities that you can plot across the x-axis. And in looking at this plot, I've got lots of data points that are here. Some that look like they are very high amplitude, and then there's a scrum that's kind of down here that all look fairly normal. So I can look at this and say, well, all right, clearly there's kind of a clustering of points above 7 that look like they're kind of outliers and maybe bad. Maybe there's some in this kind of 4 to 6 range that look maybe a little suspicious. Maybe I don't totally trust everything that's above 3. But where do I cut things out here? What amplitude can I potentially cut things out? It's very difficult, of course, when I'm just looking at all the data points just like this. And in fact, this is a synthetic data set where I've injected kind of known problems into the data set. So let me actually highlight those right now. So I've identified kind of 4 different problems, which I'll kind of describe them in a little bit later. But you can see actually that these 4 different problems pop up in different areas in the kind of amplitude distribution that's here. So clearly the stuff that's in green, you wouldn't necessarily know that there's a problem there because it's definitely mixed in with all the good blue data that's there. There are definitely a lot of yellow points that are up here that are clearly kind of the highest amplitude points that really stick out. The black data points are kind of here in a mix, and then the red data points are kind of at that top kind of threshold level where you're not quite sure whether or not it's good or bad just from blindly looking at it. So obviously this is a little bit of a problem because even seeing this picture, you should be asking yourself the question of, okay, well, at what point, if I just have an amplitude cutoff, at what point should I cut things off at? And to answer that question, we look towards something called Chauvet's Criterion. So there's a lot of text that's on here, but we'll step through it kind of step by step here. So to answer the question of at where should you establish this kind of flagging threshold, you have to go through a couple of steps. The first of which is have some sort of idea of what the mean and variance of your distribution is. If you know that, if you know it offhand, or you know it from kind of other information that you have about the data set, like what the system temperatures are, etc., that's great. You can also measure these things about your data set, right? Just calculate the mean and the variance kind of from the data points that you have. If you're looking at a particular data point, you should determine the likelihood of it existing given that the variance and mean that you calculated. So I've kind of quoted a couple of numbers in terms of significance here, describing them in terms of their number of standard deviations for a normal distribution, what's called sigma. So 3 sigma events, a kind of a 1 in 300. That's, say, fairly common, all the way up to 6 sigma, which is about 1 in a billion, which sounds like a lot, except that is, at least for the SMA, roughly the number of independent data points that you get in kind of a typical night's worth of observing. So 6 sigma events actually not that crazy or not that far-fetched. Determine the likelihood of a given event that you're looking at, and determine the number of unique data points that you're actually looking at. Like I said, you'll have to kind of understand how many unique data points you're looking at any given time, and basically calculate. First step is to basically calculate the likelihood of the event times the number of data points that you're actually looking at. If it turns out that that number is less than about half, so you are more likely than not looking at a data point that is not coming from a noise-like fluctuation, a noise-like event, you are okay to chuck that data point. If it's more than 1/2, so if odds are that there is at least one data point like that in your data set that would arise from a purely noise-like fluctuation, then you shouldn't throw it away. Basically, the long and short of it is, if there's a chance that your outlier is because of a normal fluctuation in noise, you don't want to throw it away. So in this case, looking back at our plot earlier, the threshold, Chauvet's criterion, would basically say, okay, you really want to make the amplitude threshold about 4.5 instead of something lower. Now, looking at it, you might say, well, can't you push it down a little bit further? Can't you maybe, even though you have a couple of good data points that are here, can't you clip them away? Isn't that okay? And the answer may surprise you, but it's no, and for kind of 2 reasons. So, for one, at the very best case scenario, if you, say, are definitely flagging good data, especially if you're doing it in kind of this amplitude-driven way, at best, you are throwing away good data, which is reducing the overall signal to noise that you're getting on whatever it is that you're looking at. At worst, you are possibly driving down, in this case, the amplitude of the mean distribution that you're looking at, and you're possibly producing a biased result or biasing your data because of that. So you can imagine that if I kept lowering the amplitude threshold, I could actually negatively bias the data that I've got coming out here and end up with a result that is completely spurious just because I was clipping away too much good data. So definitely don't want to do that. Obviously, having the flagging threshold so high in this case makes it very difficult to get rid of all the bad data that's there. So you might ask, well, is there another approach? And there in fact is. So what I showed earlier was just plotting versus amplitude, but you can also plot versus real and imaginary values, right? We are looking at visibilities. These are complex values. And in fact, you might see right away that some of these bad data points, rather than being kind of mixed in with all the good blue data points, now pop out a bit on their own. And in fact, if we again apply Chauvet's criterion threshold, we end up capturing a lot more bad data this way, just by kind of changing our perspective on the data. We can actually apply this further. So right now I have all the data points kind of smattered down on a single plot, but you can imagine that, well, let's say I know that each set of data points kind of belongs in a group. Let's say I have, a bunch of data points that all belong to a single baseline, and I vector average all the data points that are in there. What does that look like? And in fact, so I've kind of, I'm kind of plotting amplitude versus baseline number here, could be anything, any kind of grouping. But you can see right away that in this grouping, some of these things definitely begin to stick out more than the blue, kind of more noise-like data points. Another thing that you can do is actually scalar average. So with a vector average, you're taking the average of complex values and then taking the absolute value. And then in a scalar average, you're taking the absolute value first and then taking the mean of all those absolute values. This can be a little bit kind of riskier to deal with, or at least more difficult to deal with statistically, but instead of calculating the average, you calculate the variance. All this stuff follows kind of a typical nice normal chi-squared distribution. And again, you can see that there are definitely things that stick out in this plot that don't necessarily when we're just looking at the real and imaginary values. Finally, if you know something about a particular artifact, that it follows a certain pattern, maybe it belongs to a source that's kind of outside your field of view, but is kind of injecting some sort of problem, or that it belongs to one frequency, or you can attempt to kind of mix or modulate the data in such a way that it kind of makes it coherent, or at least coherent enough that it identifies, or that you can identify above the rest of the data points. So each of these approaches kind of give you a different handle on potentially identifying the problem. And in fact, you can use multiple views, multiple approaches to try to statistically identify where problems exist in your data set. And the only rule is that basically you want to try to make it so that you're only falsely flagging one data point kind of across all of these instances. So if I have 16 different views, or let me just look at the 4 different views I have right now, across all 4 of these views, I'm hopefully only flagging, a good data point half the time. So in each one of these individual views, hopefully there's only a 1 in 8 chance that I catch a good data point. You can kind of manipulate that a little bit, but basically that's kind of the overriding principle, is that you want to make it more likely than not that you're not throwing out, or at least equally likely that you're not throwing out a good data point. So one other thing to point out with some of these problems, obviously it can be very difficult to kind of pluck them out. They may exist below your kind of nominal threshold. And so sometimes it's worth thinking about, can I, rather than averaging data together, can I actually look at the median? And so in this case, I'm showing what the mean of the data set is versus the real and imaginary median versus the true center that's shown in here in yellow. And you can see that the data median actually is very, very much closer to the true center than the data mean is. Medians can actually be a very powerful way of effectively discarding contaminants because they are fairly robust to outliers. They do have some constraints, and they do typically come with a certain signal-to-noise penalty, about roughly 25%. But it does guarantee you kind of some protection against certain types of contaminants in your data. So it is a very powerful tool. And finally, I'll just say, so these are all kind of ways of kind of hopefully identifying problems. But if you run into a case where you're not sure, you're not totally clear whether or not there's a problem, you can always downweight data. If you see that there's a particular baseline that looks noisy, or there's a particular block of time where the visibilities just look like they're kind of going all over the place, but you're not 100% sure whether or not the data is good or not, you can kind of take this intermediate, kind of more Bayesian approach of just downweighting the data, saying, okay, this data is probably not as good as the other data that I have. There are kind of ways of adjusting weights in data reduction programs, and you can basically use that so that the iffy data is not as heavily weighted as the good data. So speaking of weights, so kind of coming back to something earlier I said about calibration. So we do rely pretty heavily on lots of different kinds of calibration in order to properly flux calibrate the data that we're looking at. And in fact, so here's kind of this fancy equation that's up here. All this is basically describing is if I have the flux density, the flux density that's measured by a given baseline, or at least that we estimate coming from a given baseline, is kind of calculated as follows, or at least this is how it's done for SMA. So we have the system temperatures that are measured for antennas 1 and 2 on the baseline. We take the product of those two values and the square root of that product, so the geometric mean of the two values. Divided by an efficiency loss factor. Typically these are kind of system efficiency values that are usually pretty close to 1. That quantity multiplied by a forward gain factor. This is basically an attribute of basically the collecting area of the telescope. So for a 6-meter telescope with 75% aperture efficiency, like the SMA dishes, this turns out to be 130 Janskis per Kelvin. Times this correlation coefficient, this rho 1, 2. We haven't talked about correlation coefficients before, but the short version of it is that you take the correlator output for the cross correlation between antenna 1 and antenna 2, and then you divide it by the geometric mean of the autocorrelation from antenna 1 times the autocorrelation of antenna 2. Basically what this number is telling you is how correlated the voltage stream from antenna 1 is versus the voltage stream from antenna 2. So you put all these things together. Rho 1, 2 kind of sort of comes from the correlator. G is something that we know kind of a priori along with eta. And then we rely on the system temperature measurements to help us flux scale the data. But what happens if these values are wrong? And here you can kind of see in this right-hand plot that there are a couple, here's some system temperatures for a couple of antennas. Most of the antennas kind of look good, but there's clearly an outlier antenna where the system temperature is about a factor of 10 lower than the others, which maybe seems not super physical. And then there's another antenna that has these intermittent outliers that seem very high. So if I were to plot the data applying the system temperature corrections, this is what that data might look like. So the bad kind of antenna data points are actually off the Y scale here, so they're kind of way, way, way above the screen here. But you can see that there are all these really low smushed down data points. And basically these are coming about because there's actually an error in the system temperature measurement, and so it's artificially kind of pushing the amplitudes down. So this can get caused by multiple things. The ambient loads that go in front of the antennas, which help us to calculate system temperature, are mechanical devices, or at least they're mechanically moved. They can get stuck. They are connected to electrical devices, which can have all sorts of errors. So all that being said, sometimes it's good to just check the system temperatures once, especially for SMA data, but for any data set where you actually apply system temperatures as part of the flux calibration. Because those system temperature values can actually really mess with the amplitudes in your data. So try to check them out at least once. I've spoken a lot about amplitude thus far, and you might be wondering, well, what about phase? And the short version of it is that you can use phase, but using phase is really, really, really difficult. So I've kind of put up the same picture as I showed earlier with the amplitude picture. And I've actually shown the phase data points on the right-hand side. And kind of now I'll show you where these different points line up here. It's very, very difficult in this very noisy distribution to see where outliers exist. And in fact, you really can only use phase as a discriminator between good and bad data when you have really, really good signal to noise and very well calibrated data. So use caution with it, because there's definitely ways, just like mucking with the amplitudes and flagging good data and amplitude can lead to problems. Flagging good data and phase can also lead to very big problems. The one exception to this is actually something called phase closure. So I have my 3 antennas here. These 3 antennas create 3 different baselines, which I'll call it, the MP baseline, the NP, and the MN baseline. And on each of these baselines, I measure some phase. and with each one of these telescopes exists an instrumental phase that's imparted onto the signal. So I can actually write out expressions for what the measured phase is for each one of these baselines, which is equal to the instrumental phase components plus this so-called true visibility phase, that is the kind of visibility of the sky. These components are kind of, the leftover after kind of adding both noise and instrumental phase components. So I have three systems of equations. What does that do for me? Well, if you add these together in this very particular way, you will actually find that these instrumental phase components actually cancel out. And in fact, you can get a quantity that's known as closure phase that depends solely on the so-called true visibility of the sky without having to worry about any calibration requirements. So that's great, but now you have to find out, well, okay, what's the true visibility phase of the source that I'm looking at? And oftentimes we're looking at sources that we've never necessarily haven't studied before or trying to look deeper at. And so these aren't necessarily known quantities. There's one exception, and that's when we're typically looking at gain calibrators. When we're looking at gain calibrators, this is kind of a slice through the image, if you will. We're typically looking at a point source at the field center, where all the light basically is coming from, all the radial light is coming from. If I take the Fourier transform of that, I get out this, which is to say, for any baseline, I expect that the true sky visibility phase or visibility real component will be positive, and the imaginary component should be 0, which means that the visibility phase, should be 0 everywhere. And in fact, you find that for most of our calibrators, the closure phase is actually 0, plus or minus this little error term that comes from just the instrumental noise. So this is in fact actually something that we do use in real life observing. So this is a program that we run called Core Plotter, which we use to monitor the performance of the array. And plotted here, kind of these white dots are the phase. And kind of for each one of these boxes, there's a minus 180 to plus 80 phase. And you can see that there's a lot of wobbling around in phase. The data was collected in the kind of early afternoon, which is the worst time for phase stability up on Mauna Kea. And so you might be asking yourself, how do you know that this data is actually worth anything? Well, you can actually look at the closure phase, which is what's plotted here on the right-hand side. And you see, even though there's a lot of phase instability on the left-hand plot, the closure phase for all the closure triangles looks beautiful. It's completely flat. So closure phase is a really great way of identifying whether or not you've got good quality data, as long as you're looking at a bright point source, so like your gain calibrators or your bandpass calibrators. There is a less commonly used quantity called amplitude closure that actually involves 4 antennas rather than 3 antennas. It's a little less commonly used because with more baselines add more kind of, you add more noise basically. But again, for a point source, you expect this quantity to be roughly equal to 1, plus or minus kind of a noise term. So this is another quantity that you can use to actually inspect your data and make sure that at least when looking at gain calibrators or something bright, that you've got something that at least you've got quality data. Moving on to kind of the next step. So I mentioned gain calibrators. Obviously you use gain calibrators and bandpass calibrators to build gain solutions. Inspecting gain solutions should always be part of your data production process. So in particular, I have a couple of plots of the gain and the amplitude and phase solutions for a given antenna, and then the bandpass solutions, both in amplitude and phase shown here for a particular antenna. These things should be very smoothly varying. Hopefully their amplitudes are all around 1. This is a good way of identifying whether or not you might have a problem antenna that needs to be flagged out. If all of your antennas look bad, it might signal that you need to make a different choice of reference antenna when building your gain solutions. One thing also to look out for from time to time is that if you see lots of phase wrapping, so you see kind of this big sinusoidal pattern, sometimes what that can mean is that the antenna position that was used at the time of observation was not as accurate as it could have been. It sometimes pops up right after we make an antenna move, we have to recalculate the position down to fractions of a millimeter, and sometimes that can take a couple of days to build up the solutions and actually get a good confident solution. So we can't fix this after the observation. It just usually means that you have to update the antenna positions, and there are programs for basically updating those. So once you've inspected the gain solutions, you should also look at the calibrated data. In particular, I usually like to look at both amplitude and phase as a function of time and frequency. Ideally, your amplitudes should look nice and flat. Your phases should all be equal to 0, as long as you're looking at a point source. And hopefully everything looks relatively smooth. Every once in a while, you will find that you will have some data points where you have larger scatter, and where things kind of maybe will start to drift. In this case, this is actually being caused by poor weather that starts to pop up basically in the late morning. And so you can discard this data. You can also downweight this data. But obviously, you don't want to treat this data identical in the same way that you treat all this kind of nice, good phase calibrated and amplitude calibrated data. So you want to do something with this data. If not discard, then at least downweight. So that's all kind of my tricks for at least looking at calibrator data. In fact, I've found that using calibrator data is typically a very handy way of spotting problem antennas. You can also look at source data. The challenge usually is that source data tends to be very complex. I mean, we tend to not look at boring things in the sky. That's part of why we do astronomy, because we find this stuff exciting and it usually has structure and kind of things to examine. Structure and things to examine basically mean that the data are complex. And when that means that you're trying to do error checking tasks, sometimes it can be difficult to find out things that are truly outliers versus just characteristics of the source that you're looking at. So a couple of things to try to check: amplitude versus time. If you see a big spike in amplitude, sometimes that can be a sign of an issue, or maybe it's a receiver or an antenna that suddenly became noisy for some mechanical failure or something like that. Amplitude versus frequency is another good one, in particular if you're worried about RFI or other sorts of kind of spectral corruption. Scalar average amplitude versus frequency, or variance versus frequency. You can sometimes pluck out when there are noisier channels, which can be caused by the atmosphere or caused by inefficiencies in the correlator, so on and so forth. Another one that can be a little tricky to use, but is sometimes very helpful, is actually looking at amplitude versus baseline, or amplitude versus UV distance. Typically, when you look at baselines of longer and longer distances, they tend to resolve more and more flux out. So you typically see this trend of decreasing amplitudes as you go to further and further UV distance. That's not always true, and there are definite caveats to that. But it's a good kind of rule of thumb for just checking the quality of a data set. And again, phase sometimes can be helpful. You just have to be very careful with it. And more often than not, I find that I usually won't look at phase at all, because it's not very helpful in detecting problems, particularly on noisy data sets. So hopefully that gives you some ideas behind the kind of general philosophy that you should be using when you're approaching flagging your data sets. A key here again is Chauvet's criterion of try not to flag any good data, because if you flag good data, you run the chances of biasing your data sets and basically getting out results that are no good. Yeah, thank you very much.